All right, welcome everyone. Today I'm delighted to have Allison Jaynes speaking with us today. Allison Jaynes is an associate professor who joined the faculty at the University of Iowa in 2017 after receiving a PhD from the University of New Hampshire and working as a researcher at the University of Colorado. Her research focuses on intermagnetosphere particle dynamics, including the ring current and radiation belts, and how these two regions connect to the upper atmosphere and to the aurora. She has served as a co-investigator in NASA's Van Allen probes and Voyager missions, and is currently serving as a member of the Heliophysics Advisory Committee to NASA headquarters and as a member of the Heliophysics Decadal Survey Steering Committee. She previously served as a co-chair of the Geospace Dynamics Constellation Science and Technology Definition Teams, the GDC Science and Technology Definition Teams, and was awarded an NSF Career Grant in 2020. Currently, Allison is advising 1 postdoctoral research and 4 PhD students, and was recently awarded the University of Iowa Postdoctoral Association Mentor Award. She is deeply committed to equity and inclusion in STEM and is passionate about promoting active learning and positive team dynamics. Today, Allison will be speaking to us about the dynamics of the Earth's radiation belts from loss in the atmosphere to particle precipitation in the atmosphere, one of a series of talks on energetical particle precipitation that we will be having this summer. With that, Allison, if you would like to take it.
Okay, thanks, Kyle. So I've got construction going on across the hallway, but I've negotiated with the contractor. They should be quiet for the next hour. So hopefully you're not going to hear concrete saws in the background. If so, I'll have to figure something out, but I think it should be good. So thanks for inviting me to speak today about this topic. This is really based on a book that Masha Maria Yusinova and I edited that was published a couple of years ago. But I wanted to start off with just this visual of the aurora here. Now we're looking at a flyover from the International Space Station, and you can see lots of really beautiful arcs and rays in the aurora as we go by. But you can also see at some point in the movie, if I back it up here, if you look just equatorward of those arcs, you can see some flashing down here. This is pulsating and diffuse aurora, and this is really a visual indication of precipitation from the magnetosphere. So it's kind of fun to start with just that. I also wanted to go over this idea of our solar wind as being sort of the driver of all the stuff I'm about to talk about. So I've heard this said before, but the sun is really the cause of everything interesting that we study. So it's interesting to see what the effects are when you get this into a visual form. We really see that the sun creates energetic particles, it creates waves, it creates plasma boundaries that we care about, it creates precipitation, and then of course it creates aurora as well. The only thing I have against this video is it doesn't really show plasma waves. So if anyone wants to indicate that to Goddard, the visualization studio, if they could add some plasma waves in the intermagnetosphere during this whole process, then it would be pretty much perfect. So Kyle invited me to talk about this book, and you can go look this up on the Alsphere website if you're more interested in what I'm talking about today. I really wanted to go through some of the topics that we discuss in the book and from all of our wonderful chapter authors, and then maybe go through just some highlights of things that we haven't really talked a lot about before, or some things I thought were really interesting to go over today. So I'm not going to summarize the entire book because these are huge, long chapters, and they're really interesting to go read in their own right. But I am going to just go through some highlights and actually some things that weren't really published by the time the book was completed. So there's some new studies as well that I wanted to go over. So the topics I'm going to cover that the book covers are kind of broken down into 3 categories. The first is loss processes. So basically what happens in the magnetosphere. We're going to talk about outward transport and magnetopause incursions, talk about wave-induced losses through different resonances. And then we're going to go through platforms for observing loss processes. Of course, we use satellites. That's basically the focus of the first part here. But we're also going to talk about nanosats or CubeSats and suborbital observations, ground-based observations like ISR networks and VLF receiver networks. And then finally, the last couple of chapters are focused on the effects on the atmosphere. So how high energy precipitation affects energy deposition, ionization, and atmospheric chemistry, and some of the modeling that's been done in those areas and diagnostics that we can use to look at that. Okay, so again, I'm not going to hit everything that goes on in all of these chapters, but I did want to just do an overview of what we came up with for this book, because we really saw a need to have all of this stuff in one place and chapters that could refer to each other. And so we wanted to, that was the idea behind collaborating with these authors to get this book published. I'll also say that editing a book is really not a special skill. All you have to do is mercilessly hound your chapter authors into getting something on paper. Anyone could do it. So if you're interested and you have an idea for a book, talk to me and I'll tell you how it went. But it's a really kind of a fun process and a really nice product in the end. Oh, I also wanted to say that there are previous talks in this seminar series by a number of people that went through energetic particle precipitation as well as radiation belts in general. That was Drew's talk. And then there was a whole series last August about different wave modes. We did ULF waves, VLF waves, EMIC waves, and then Lauren had a really nice talk on energetic electron precipitation. So I'm trying not to cover things that were covered in those talks. I actually went through and reviewed most of those talks in preparation for this, just to make sure I wasn't duplicating a lot of information. So although we're going to kind of go broad and not deep in this talk, if you do want to know more, there's all these other seminar series on the YouTube channel that you can dig into. Okay, so the first topic that we covered in the book was this idea of magnetopause incursions, as well as outward radial transport. This chapter was written by Drew Turner and Sasha Ikorsky. And the motivation here was to kind of start outward and work in. So we're starting at the magnetopause, and then we're kind of going through the inner magnetosphere, and then finally down to the atmosphere. And the motivation for studying these types of loss processes specifically is to understand something we call flux dropout events. I'm showing a good example of that here from the book chapter. This is energetic particle data from Van Allen probes, and we're looking at several different energy channels up into the multi-MeV range. And you can see this sudden dropout that occurs at all of these energies. It really persists for a couple of days before this thing starts to build back up. And it also covers a large range of L shells, right? So you see this drop off deep into the inner magnetosphere down to low L shells. And in fact, the 6 MeV particles never recover after this event. So the idea is to understand the relative role of something like magnetopause incursion together with outward transport versus a local process like EMIC wave-driven loss. And to understand what the relative roles are of those two things, we need to really understand magnetopause incursions. Okay, so here's a cartoon from that chapter showing ideal phase-space density radial profiles. Of course, if you look at these in real data, they look a lot messier than this cartoon, but this gives you the idea of what things should look like in an ideal world. So here we're just showing this magnetopause incursion phenomenon where you get a sudden pressure pulse to the dayside magnetosphere, and you end up with a last closed drift shell that's much closer to the Earth than it had been previously in a small enough time scale that things cannot adiabatically react, and you get sudden losses. This cartoon here is kind of showing the time series format of what that would look like over time. So you get potentially this outward radial transport happening from T1, T2 to T3, and you get these peaks that are forming as a result of something like a loss out at the outer L shells, and this can really drive that outward transport. You see the bigger arrow here. You can have some serious outward transport happening as you get that loss at the outer L shells. I will note that we're using this term magnetopause incursion in place of magnetopause shadowing. There is a good argument for that because the shadowing kind of implies that you're just losing everything all at once, whereas incursion is really what we're seeing because you sometimes have a difference in energy that's affected by that magnetopause location due to that diffusion timescale outward, or you have losses at some pitch angles and not others. And so the incursion, we're meant to change the vocabulary a little bit and use incursion instead of shadowing. So the types of magnetopause losses that you can get at that outer boundary, this is a nice schematic that they put together for the chapter, which shows the different quiet to active times and what can happen in each. So the first one is just sort of typical, maybe quiet or moderate activity, where you always have some particles that are lost from waves, Kelvin-Helmholtz instability, for example, or transients like flux transfer events. And you can see here that just the region of the trapping boundary, this pink line, you will get some magnetopause incursions and some losses as a result of those boundary effects. The second one is when you have a sudden pressure pulse. You have a sudden inward motion of that magnetopause or last closed drift shell, and you can get sudden losses on any drift trajectory that intersects with that new location of the magnetopause where it didn't before. And again, if this is on a fast enough time scale, then you don't have time for adiabatic reactions. And so particles can be lost very suddenly. And then the third type here is often seen together with the second, and this is drift shell expansion, or what some people call DST effect, where you can get this expansion in your location of your drift shell, and that's going to also intersect some of those trajectories with the magnetopause and lead to losses. And again, we often see observationally that both of these two things happen at the same time. I will note a couple of other drivers to this whole process that can play a role. The first is drift orbit bifurcation or drift shell splitting. So Mary Hudson had a nice paper in 2015. This is just showing ULF wave power and the azimuthal electric field, and together with magnetopause location in black here. And there was a sudden inward motion of the magnetopause to inside of GEO during this October 2013 storm event. And their results found that bifurcation was important to obtain the observed losses. So not just the inward motion of the magnetopause and the enhanced drift orbits, but also the drift orbit bifurcation. Yukorsky et al. Had a couple of nice results, including this 2014 result, where they found bifurcation leads to an order of magnitude increase in over radial diffusion rates. So we're seeing that there's quite a significant effect due to that drift orbit bifurcation. And as well, the magnetopause incursions can create some of the morphology that we see in the outer belts. For example, this idea of remnant belts or double outer belts that has been reported before. I'm showing here a figure from Goldstein 2016, where you can see the peak of a remnant belt or an inner outer belt, and then a peak of a second outer belt above that in L star. And there's a dropout that occurs here, but the remnant belt actually stays fairly well protected and continues to slowly show loss over time after that dropout has occurred, whereas the second outer belt had to be built back up again. So this was a really nice study on what can happen as a result of dropout, but also what can happen as a result of these magnetopause incursions, creating and then sustaining this remnant belt and creating a second belt on top of that. Okay, so then in this book, we had a few chapters, 3 in a row, that dealt with plasma waves in the magnetosphere. And I'm actually not going to talk a whole lot about this stuff because this has just been covered over and over again by some probably more expert people than myself. So I'm just going to show the cartoons of the plasma wave distribution in the inner magnetosphere together with real data because the cartoon never really gets across how messy real data is. So I like to show this figure from Suratani and Smith, where we're looking at all of these different wave modes kind of at once together at play, except for EMIC waves, which you can't really see on this frequency scale. And I'll note the chapter authors. So we had ULF wave-induced losses that was covered by Brito, Halford, and Elkington. We had a nice chapter on cyclotron wave-particle interactions, which covers VLF and EMIC wave modes by Blum and Brenneman. And then we had magnetosonic bounce resonance interactions covered by Chen and Bortnick. So I encourage you to go read those chapters for sure. I'm just going to go over a couple of highlights that we didn't really get to put into the chapters that have sort of caused some intrigue in the last couple of years. So the first one is this idea of EMIC wave-induced precipitation. This figure on the right, of course, has been looked at over and over again, very famous figure by Usanova, 2014, where they're showing this idea that EMIC waves are really causing losses at lower pitch angles. And yet we can see a decrease in the core population when you look at spin averaged electron flux. So for example, right here in the spin averaged data, you can see sort of a drop or a decrease and flux at a wide range of L shells. And then here in the pitch angle distributions, you can see the narrowing of that pitch angle distribution quite dramatically at the same time that we see the presence of EMIC waves from ground stations. And this has already been talked about quite a bit and was a very nice study all on its own. But what's followed on from that is this idea of trying to figure out when EMIC waves are occurring and what kind of precipitation that they are causing. And one of the things that has come up is this open question of, can EMIC losses account for a substantial part of the total radiation belt loss? I think that's definitely still very much an open question because we have studies like this one here. I'm showing this plot of total EMIC wave events, in conjunction with post-satellite measurements, and then EMIC wave events that are associated with this relativistic electron precipitation. And we see that there's only a subset of EMIC events that are actually associated with relativistic electron precipitation. And that makes you kind of wonder why we're not seeing that precipitation all the time that we observe EMIC waves. So there's this still open question of really what is driving the precipitation, what are the conditions under which we actually get efficient precipitation, and can that account for a larger fraction of radiation belt losses? I know that recently we've been talking a lot about looking for signatures of EMIC wave losses in phase-space radial density profiles. For example, this study from Spritz 2017, where a deepening loss in the phase-space density profile can indicate local losses, most certainly due to EMIC waves. And so this is one diagnostic tool that we can start to use to find maybe the prevalence of EMIC waves. But we're also going to have to match that, like this study here, with precipitation to understand what role they play in the overall precipitation. Okay, I also wanted to bring up a study that was really not yet published when we were able to complete the book. And this is probably no surprise. I'm going to bring up pulsating aurora, not once, maybe twice, maybe 3 times in this talk. So this is the idea that chorus-induced precipitation can occur over a wide energy range. This was a nice study from Miyoshi 2020 that showed a chorus that propagates to high latitudes can cause precipitation at higher energies. And so you kind of get this full energy spectrum of precipitation, which would cause pulsating aurora as well as higher energy precipitation, what we would call microbursts. So he came up with a chorus model here that showed the rising tones as well as the precipitation that occurs as a result. And I want to show the cartoon from that paper because it really just very clearly shows what the idea is here. We get a change in resonance energy when these chorus waves are existing at the equatorial location versus when they exist at this off equator position. And so when they're at the equatorial position, you can get resonance with tens of keV energy of electrons. Great. We have things like diffuse and pulsating aurora that are caused as a result. When they go up to higher latitudes, that resonance condition changes. It's not the only thing that can change the resonance condition, but it does change the resonance condition. So you get interaction with potentially up to things like relativistic energies. And so that's where you can create some of the phenomenon like microbursts or high energy precipitation. In his simulation, they show this idea of the rising tones themselves creating the precipitation, and they show that across the energy range that we're talking about. So here's a result from 9 keV electrons, and this is showing sort of what you think of as a pulsating aurora patch. There's the patch on and the patch off phase there. But the precipitation itself persists when the patch is on. So you can kind of see it never goes down to zero. There's always some precipitation when the patch is on. If we go up to higher energies, so 100 keV or even up to 2 MeV, we see that we also have precipitation at those higher energies during the time of low energy precipitation, but they're more discrete bursts. Okay, and this is really what we see in the observations as sub-second modulations, quick discrete bursts, which you would call microbursts, right? So we see microbursts sort of in concert with these larger low energy patches of precipitation. And this was a really nice study just showing that you can create this full energy range from chorus wave interactions. Okay, one last thing on precipitation from VLF waves. Microbursts, again, have been a really big topic of interest lately. And I wanted to highlight this study here from Mike Shumko in 2021. I don't think this movie was actually in the paper. I think this was just an additional movie that he sent me. But the paper is essentially the same thing. It's covering this transit of SAMPEX across patchy aurora and pulsating aurora. Patchy aurora is sort of like pulsating aurora that doesn't pulsate. It's kind of confusing. But if you look at this movie, you'll see that the microbursts are occurring right here. So right when that SAMPEX satellite passes over these patches, these static patches right through the center of the field of view here. And we get all of this microburst activity in SAMPEX. So this is an example of going back to an old data set and finding something completely new within that data set. And I think that he's found a number of events similar to this since this paper was published. So it just really opens up the scope of what we understand to be microbursts in their relation to some of the diffuse aurora. I also want to highlight Sadie Elliott's paper. I think it's still in review. I haven't seen it come out yet. And this is a figure showing some multi-spacecraft observations where they tried to constrain the microburst precipitation region and the chorus generation region, or the chorus power region. And so you can see here that the chorus extent in dark blue and the microburst extent in green, they don't quite overlap, right? They're not completely on top of each other for this particular event. So there's something going on where we're seeing microburst precipitation some of the time, and then there's still chorus occurring, but we're not seeing that microburst precipitation the rest of the time. So this is a really interesting multi-satellite study that's looking at that question of when and why do microbursts occur. And I would also argue that another important question is how often are they concurrent with high energy pulsating aurora? Okay, so then we moved into platforms to observe losses. And we did not really cover satellite missions because those had been covered in earlier chapters. We wanted to highlight some of the new and different things that are being used in our field. So this chapter was all about nanosat and balloon-based studies of loss. They did not include rocket in the title of this chapter, but I will forgive them because they did talk about rocket observations within the chapter. So this was put together by John Sample, Robin Millen, and Leslie Woodger. And they highlighted a lot of the platforms that you'll be familiar with. So I'm just going to kind of quickly go over some of those here today, like the Barrel mission. We've heard a lot about that. There's been a lot of great results that have come out of that. Another important one has been the CSSWE CubeSat out of Colorado, PI Shinlin Lee. And they were sort of one of the first, rad belt CubeSats that was able to give us some really good scientific information. You can see here the coherence that we see between the CubeSat instrument on the top row and Van Allen probes on the second row. There's this really nice coherence between the low altitude measurements and the equatorial measurements. We got a lot of great science out of CSSWE. But I just wanted to highlight a few of the conjunction studies that they went over in their chapter, because this really shows the power of these different types of suborbital and smaller satellite missions. You're not always going to get groundbreaking scientific results with the mission itself alone, but by using them in conjunction with other things, you can say some really important things about the environment. So this first one is from Brett Anderson, 2017. And this was trying to get at the spatial scale of microburst regions. They used Beryl, Firebird, and AC6. And you can kind of see the boundary there of the microburst region that they came up with for this study. And so this is just one of a few studies that have really been trying to understand and constrain what that spatial scale is, both in terms of radial distance as well as MLT for different types of events. And then this Blum 2013 study to investigate precipitation bands used CSSWE data, so to find the precipitation bands up top, together with Beryl looking at precipitation from the Beryl balloon directly. And this was an interesting study because there were two precipitation bands that were observed on CSSWE, sort of in follow-on orbits, but yet there were three precipitation periods or bursts that were observed in Beryl. And so this is one of the many studies that have shown that the precipitation regions do not stay static, they change over time. And so you'll often observe them with some platforms and not others, even though they're nearby. And so just wrapping this all together and our understanding of how precipitation regions evolve is going to be really important. And conjunction studies like these are what has been driving that understanding. Brenneman 2017 also looked at observational evidence of chorus causing microbursts. So they used Van Allen probes together with Firebird, and you can see the microburst flux down here and the chorus amplitude up here, and really showed that they're kind of going through a region of high amplitude chorus at the same time that you're seeing a region of microbursts precipitation with Firebird. So that was a really nice study using one of our larger assets together with one of our CubeSat assets. And Jaynes 2014, they used Van Allen probes again with CSSWE, the little CubeSat going through the radiation belt L shells, and looked at electron lifetimes during a quiet period and quantified what some of those electron lifetimes actually looked like when nothing was going on. So this is one of those really, really boring times in Van Allen probe's early history, but it really was able to get us a good look at quiet time decays in these high energy electrons. Okay, so then we moved on to look at some ground-based platforms that we can use to observe losses. And this chapter was put together by a number of authors there, and we wanted it to go over the incoherent scatter radar methodology. They did a really, really nice job. This is a very comprehensive review paper. If you're interested at all in ISR methodology, the modeling that takes place, and then the observations that you can get out of it, I highly suggest going and reading this chapter. I did want to take this figure from their chapter that really shows all of our assets that we're using in space and on the ground. We can see VLF transmitter and receiver paths here. We can see the radar giving us a mesoscale view. We can see optical emissions and X-ray emissions that might be captured from ground-based imagers or space-based imagers. And we see the space-based particle detectors themselves, which are getting the smaller in situ measurements very directly. So lots of things that we're able to use to diagnose these types of events. I also stole this figure from my student's poster, Riley's poster, because it kind of nicely illustrates what a radar looks like and what it's doing, sending out these pulses into the ionosphere, measuring the electron density and the backscatter that comes back from the electron density, and then from there able to make some assumptions about what that electron layer looks like. So I did want to again bring up pulsating aurora and highlight two observations that they showed in this chapter, and they're both of pulsating aurora with ISR techniques, right? So they're looking at pulsating aurora from the point of view of ISR, and the reason is because we can try to get an idea of the energy in this case. We see signatures of high energy precipitation, which you can read as low altitudes during times of pulsating aurora. So this first case study, Hosokawa and Ogawa, 2015, saw this drop in electron density altitudes during times of pulsating aurora. You can see on the kilogram up here, they've labeled these periods as pulsating aurora, and we see that overall lower altitude in the electron density. And we also notice that one period of pulsating aurora is clearly more energetic than the other. So this later pulsating aurora is certainly more energetic than the earlier one. And so we can use that to sort of diagnose different types of pulsating aurora, energetic and not so energetic. This Miyoshi 2015 study saw a decrease to very low altitudes. So an increase in energy during a pulsating aurora event that was very sudden and sort of had implications for atmospheric consequences as well. And I wanted to show some ISR observations from our recent LAMP rocket launch mission. So here is the long-term full night view of our ISR observations. And you can see multiple times in which we have low altitude precipitation or high energy precipitation. This alone kind of gives you an overview or an indication of how often we're seeing high energy precipitation. And these were all associated with pulsating aurora, I'll say. But what we can do with the radar data is we can take that electron density by altitude and invert it so we get the incoming electron spectrum. And from there, we can look at energy directly. And so here we're breaking it down into different energy bands, less than 30 keV, greater than 30, greater than 50. And we get an idea of throughout the night when we saw the highest energies occurring with the pulsating aurora. For example, this time here centered around 1330 UT, we can see that there's a huge increase in the flux of greater than 30 and greater than 50 keV electrons. So this was a very highly energetic event that we're still studying right now. Okay, so then we went into atmospheric effects and signatures of energetic particle precipitation. This chapter was put together by Robert Marshall and Chris Culley, and they looked through the effects and the modeling that take place when looking at these processes. So the effects, for example, ionization, Bremsstrahlung emission, particle backscatter, optical emission, and then chemical effects. And the modeling part, they looked at scaling and Monte Carlo methods for determining kind of what the energy deposition would be at various altitudes. I like this figure quite a lot. I've stolen it many times, but it's essentially showing you the peak energy deposition by altitude for different incoming incident electron energies. And so we see that, of course, as the energy increases, the peak decreases and gets down to lower altitudes. The peaks here are then plotted just on a simpler energy spectrum over here. So you can kind of see that relationship very clearly. We see that multi-MeV electrons can get all the way down to below 50 kilometers. And this one is interesting. What they've done here is show that there's a pitch angle dependence, especially for high energy electron precipitation. So we're looking at 3 and 10 MeV in these traces down here. And you can see that even within the loss cone, a small change in pitch angle actually translates to quite a dramatic change in where that energy gets deposited. So it can be a difference of 10 kilometers or more versus if it's on the edge of that trapped boundary, or if it's very low down in the loss cone. So this has implications for why we need pitch angle resolved information about precipitation, not just some kind of average. Okay, in their chapter, they went through the effects and the modeling, but they also went through other diagnostics. I'm not going to really talk about those effects because Bob's speaking in a couple of weeks, I think, so he's probably going to go through some of that. But I'll talk about the diagnostics that they mentioned really quickly. One of those is this Bremsstrahlung emission. So there is a funded, nearly ready to go CubeSat called Apex, which will be using this AXIS instrument. We'll be looking at this Bremsstrahlung emission coming up from the precipitation that happens in the ionosphere. You can kind of think of this as a barrel balloon, but from above. So we're looking at the precipitation causing Bremsstrahlung emission upwards rather than downwards. So there's some benefits to that. And so this is sort of a mesoscale view of precipitation that we'll get from this CubeSat mission. The middle one here is showing a rheometer, just with some pretty aurora in the background. But the rheometers are really important for understanding the ionospheric absorption or essentially density that we see above in a field of view above the rheometers. And the nice thing about rheometers is they can actually be carted around and set up various places pretty easily, pretty quickly. And so they're almost like mobile stations that then can sit there and get information for hours and hours at a time. This one was set up at Poker specifically for the LAMP mission. So they're somewhat portable. And then of course the real CubeSat mission led by Robin, and hopefully we'll get some nice pitch angle resolved information about precipitation from that as well, because one of the points they made in this chapter was you really need pitch angle resolved observations to understand the real losses that we're seeing. Okay, and then finally down here, I'm highlighting the projects led by Eric Donovan and Emma Spanswick, which is called T-REX, or Transition Region Explorer. And this is sort of a new network of ground infrastructure that's going to be deployed at these various sites that will get different information about slices in the ionosphere by altitude from different types of imaging and rheometers and spectrographs, so that put all together, we can kind of have this really full picture of across spatial scales and across altitude, kind of what we're looking at in terms of precipitation, auroral dynamics, radiation belt losses, and things like that. So this is a really, really nice project that hopefully is going to keep going, and it has a lot of momentum behind it. So I'm very hopeful that we'll see a lot coming out of that in the future. Okay, so then the next chapter was focused on VLF observations of energetic particle precipitation. And it was put together by Aaron Hendry, Mark Clivard, Craig Roger, and Mark Engebretson. And they really focused on this ground-based network of VLF receivers, which takes advantage of our existing ground-based network of VLF transmitters and sort of captures the ray path of these rays that are getting sent out by the transmitters. And here's a little cartoon just showing kind of how that works. The receivers are capturing that signal. And if we do have energetic precipitation, it kind of causes a disturbance in that ionosphere. And you can see that through a change in the ray path. So that's the idea. It's a pretty simple notion, but it can be very powerful when it's used for some of the case studies, as I'll show in a second. The specific network that they work with is called Aardvark. So some of the case studies they highlighted in this chapter include this one by Hendry, 2016. So this was a case study looking at EMIC wave-driven relativistic electron precipitation. So they showed that there really was relativistic precipitation occurring with conjunction of an EMIC wave, which was a nice observational validation to see. They also looked at these events statistically. So they looked at a number of EMIC wave precipitation events. And they saw that most precipitation events were associated with helium band rising tones of PC1 waves observed on the ground. So that's kind of interesting, just then they were able to narrow down the type of band that was associated with most of the precipitation that they saw. This case study, this was a figure in the chapter that doesn't really come from Mark's paper, but it's sort of adapted from Mark's case study. So this was a case study in 2013, in May 2013, which showed rising tone EMIC waves here captured on the ground, and then a number of stations in the receiver network. And you can see those stations up above here. So each of these red paths is one of the station extents that they're using between a receiver and a corresponding transmitter. And the interesting thing here is you can actually see a westward propagation of the precipitation. So when we're looking at the Sedonkala receiver over here to the east, we see the precipitation occur first. And then we can move over to St. John's and we see the precipitation occur a little bit later. And then if we keep moving west, I believe it was Churchill Station that they used. And this is the precipitation is kind of last. So you can kind of see this westward propagation of the EMIC wave precipitation, which makes sense. You also see that as the EMIC wave evolves in MLT westward, we also see a change in the amount of precipitation or the duration of precipitation, right? So these two are showing shorter durations, whereas this Churchill station showed a nice long extended amount of precipitation. So this is interesting in terms of our understanding of how EMIC waves evolve, maybe as they drift and propagate along in the magnetosphere. Okay, so the final chapter was all about atmospheric chemistry effects of energetic particle precipitation. This was put together by Miriam Sinhuber and Bernd Funke. And I'm not going to go into this in detail either, because we're getting an entire talk about this soon as well. So just to say that if you had any confusion about what is this whole atmospheric chemistry process that takes place, there's a really, really nice walkthrough of how that works in this chapter. I really appreciate this as just a community resource going forward, because they did a very nice job of just laying out exactly how what we view as radiation belt loss actually plays a role as an input in another system, in the atmospheric system. So this is a schematic of just showing exactly how this kind of thing works. We get energy deposited by precipitating particles, whether they're plasma sheet type aurora, ring current or radiation belt, and diffuse aurora, which kind of has higher energy and deposits lower, or even SEPs, which can deposit their energy way down in the atmosphere. And as a result, we get chemical constituents produced. And these are referred to as nitric oxides or hydrogen oxides, or you may have heard the terms NOx and HOx. And we get those produced at different altitudes. They really only become important when they interact with ozone down at lower altitudes, but they can get circulated downward, especially during the polar winter when we have the polar vortex in full swing. And so this is a slide I stole from Cora Randall's a number of years ago, because it's a really nice visual of what's going on when we have these interactions. So we know that NOx catalytically destroys ozone, and you can visualize that as sort of the NOx Pac-Man eating up the ozone molecules. So this is kind of why we find it so intriguing to study from our point of view. This is, again, how magnetospheric precipitation affects our atmospheric constituents. And there's two types of effects that we talk about when we go through this whole process. The first is called the direct effect, and this is when the electron has enough energy that it can deposit directly into the stratosphere. These are things like your SEPs or your multi-MeV electrons. So if we have a direct penetration to the stratosphere, we can create NOx directly at that altitude, and it can start catalytically destroying ozone immediately. If we have a lower energy electron, they'll typically deposit their energy higher up, and we get what's called an indirect effect, meaning we need some process to take the newly created NOx and circulate it downward before it has an effect on the ozone. So as a result, we can see things that take months to set up and and effects that last for months as well. So local ozone losses that persist for months of time. And it's kind of due to this combination of the direct effect and the indirect effect. And this is all based on our full spectrum of loss that we get from magnetospheric particles. Okay, so that's the end of the review of this book. I did want to mention to check out the next few talks in this series, which go into some of these topics in a little more detail. And I wanted to end it there and ask for any questions.
Thanks, Allison, for a great talk. If anyone has questions, they can put them in the chat. I have a quick one. We've had SAMPEX, we've had a number of CubeSats and the radars and Van Allen probes. So what do you see is next for energetic particle precipitation and studies in our field?
Yeah, that's a good question. I think we're only starting to get at this, the power of using the conjunction measurements. So there's some stuff in the ISR chapter where they're looking at Van Allen probes wave observations at the same time that with the conjunction with the ISR, you're looking at precipitation. And so things like that can be really powerful because you're able to, see both the waves that are creating the precipitation at the same time that you're seeing a really, really detailed look at the energy spectrum of the precipitation from the ground. So a lot of these conjunction measurements that I've tried to highlight throughout this talk, I think are just the beginning of what we're able to do with these techniques. But I think also the prevalence of suborbital observations is maybe becoming more popular. And I think that should continue because some of the balloons and the rockets and some of the ground-based networks as well are where, magnetospheric physicists tend to be a little uncomfortable with. They don't use those platforms as much, or they're not as sure about the data, but those can be where we get the real insights, I think.
Excellent, thank you. I think it would be great if we could get all those working together instead of everything always somewhat out of phase and we never get the conjunctions perfectly. So that brings today to an end, unless I interrupted you.
No, there's just a question. Do you want me to read it?
Yeah, it just popped in. So if you want to.
Okay, so there's a question. If the material of the book can explain how relativistic electron fluxes after the 3 types of magnetic storms can restore when intensity of electrons restores after storm till pre-storm level. Yeah, so there's some talk about the dropout events and what happens in terms of wave particle interactions to create acceleration periods that happen typically after those storm periods and where you get that resurgence of radiation belt fluxes. So there's a lot of discussion that I kind of skipped over, mainly because it's been done in previous talks, and you can kind of go back to those MOS talks I highlighted at the beginning and watch those because they're actually quite good.
Yeah, I think, Allison, you have a great paper that shows the interconnection between them all, the source, the seed, and the relativistic population. And as you say, we have a number of talks from earlier in the seminar series which cover that.
Yeah.
We do have another question that came in. What is the contribution of ionospheric heating via radiation belt precipitation? Is it a large component?
Yeah, that's a good question. That's one of the reasons that I think the sort of typical CDAR and GEM communities should sort of be talking a little bit more to each other, because we don't really have a good handle on quantifying some of these things. So, as much as the GEM community and radiation belt community kind of likes to ignore what happens in the ionosphere and the measurements that we take of the ionosphere, I actually think they're really important to understanding our system and the heart of our system. So I would like to see a lot more collaboration in that respect. That's another plug for these white papers that are being asked to be contributed right now. I think one of the nice things that could that could be put in by many different people is this idea of getting the system science going, or forgetting about these artificial boundaries and having researchers work together that come from different areas, and the mechanisms by which NASA and NSF could foster those connections.
Excellent. So that question does lead nicely into next week's talk, who you've already highlighted. Miriam Sinaber will be discussing energetic electron precipitation into the atmosphere, following on from Allison's introduction of this book and that specific chapter. So with that, thank you very much, Allison, and I hope everyone has a wonderful week.
Yeah, thanks.
Bye.